Okay, I think it's working now. It's a bit blurred. Anyway, as I was saying, we have mentioned the incomplete beta function and the regularized beta function with its properties. And I was talking about the digamma and polygamma. The digamma for the first derivative of the gamma function. It's actually the derivative, the gamma function divided by the gamma function. So it's, remember, the gamma function increases very steeply. So the derivative is also large, it becomes a large number quickly. But if I divide by the gamma function itself, is growing even faster, then this function behaves much in a much more friendly way. Okay, actually, you can see that it's decreasing, for instance, somewhere. If you need higher order derivatives of the gamma function, then again, there is a whole family of polygamma functions. So remember, di means two and poly means many. So the second, third, fourth derivative of the gamma function can be defined as a family of special functions that cannot be defined in an easier way, but it has applications. So this is the digamma, and in general, we can say the nth order polygamma function. So let me call it with the same n. So the polygamma function of order n would be the nth derivative of the digamma function. Okay, so it's the nth derivative of this digamma function. So if you need if you need the derivative of the gamma function itself, you can just calculate it from this one, right? The gamma function had a very important recurrence relation. If you remember, that tells me that. So for the gamma function, we saw that gamma of z is z plus 1, and right, z plus 1 is always z times gamma of z. Notice that here for the digamma polygamma, I'm using x because the applications are typically for the real axis, and that makes the properties a bit easier to discuss. And there is a recurrence relation that can be found for the digamma function. It has a recurrence that looks like this. If I want to calculate the digamma function at some value of x plus 1, the value would be the same as the value of x plus 1 divided by x. Okay. So it's really not, this is not really decreased, right? For positive x, this is going to increase. If you look at it, every time you go to the right one unit, it will increase a little bit. Each time less, but remember this series doesn't converge. So actually this function grows very slowly, but never stops growing. So an interesting property of the digamma function is that it is also the the result of the sum. Let me write this first, of an infinite sum. Well, for any value of x, the diagonal function will be this constant that we introduced in the last class, the Euler-Mascheroni constant. Sorry. Yes, Euler-Mascheroni constant with a minus sign plus this infinite sum. The sum over k from 0 to infinity of 1 over k plus 1 minus 1 over k plus x. Okay. And notice that I put this in parentheses because the first sum doesn't converge. If you try to sum only this term, it doesn't converge, right? It's a decreasing series, but it grows too slow. So to sum it to infinity, it will diverge. So here we take the parentheses because we take the difference for each of the terms, and then this series does converge, and it converges to the diagonal function. And I don't have a proof for this, but it has applications. And if you have some infinite sums can be converted into a diagonal function, and then you can well, work with that as a function, or if you need the value, you could evaluate the diagonal function with numerical methods, etc. So you see, for example, combining the values at the diagonal functions at two values of the variable, we call them x and y, you can see that the difference of the diagonal function, diagonal function at x minus the diagonal function y, both are, let's assume both are real numbers. Then, if you do this difference, the Euler-Mascheroni constant disappears. These terms disappear one by one, and we will get the sum from k equals 0 to infinity of 1 over k plus y minus 1 over k plus x. Okay, so this can have some application. Let me give you an example. So an example of this application. I'm going to write a bit weird because I'm worried about the camera. Okay, so imagine I have this infinite sum. The sum from k equals 0 to infinity of minus to the power of k over a squared minus k plus 1/2 squared. So we already discussed a method in which we use contour integration over a square shape, right? And find the residues of the function of the summation variable along the contour multiplied by some trigonometric or hyperbolic function, right? Depending on what you get. I didn't discuss all the cases, but I gave you a formula sheet where there are 4 cases without the power of the -1, with the power of -1, with the function evaluated at k, or the function evaluated at k plus 1/2. There are four equations that you can see in the formula sheet. But one problem is all these equations require a contour that goes to infinity. That means I need to, I will have poles from -infinity to infinity, and the sum will become can only be calculated from minus infinity to infinity, right? And if the function is even, well, sometimes we can separate the sum into the sum of the negative terms plus the sum of the positive terms, and then if we know how to do that, or if they are equal, like in the example that we saw, if they are equal, we just can calculate the total and divide by 2, something like that. But in a case like this, okay, that happens when it happens when there is a kind of even function. But the problem is, in some cases, if you try it with this function, you will notice that the sum is 0. The sum starting from k equal minus infinity to infinity is 0. So from the contour integration, we just get 0. We don't know what part, what is the sum from 0 to infinity and what is the sum from minus infinity to 0. Yeah. And well, it's probably you can separate this and see that the two sums are equal with opposite signs, and then they cancel. Now, in this case, we can use the digamma function. To do this, let's we need to remove this minus to the power of k. We can do that by just separating the even terms and the odd terms, and then there will be a sum with a plus and another sum with only a minus. Let me do that. So here we will have both sums starting from k equals 0 to infinity. So let me put that together. And then well, now I'm still calling it k, but I am really changing from this k to the k divided by 2, something like that, so that like the even terms will be 2k and the odd terms will be 2k plus 1, right? So the positive terms will become the sum of 1 over k squared, and here, yeah, we change from k to 2k, sorry. 2k plus 1/2 for the even terms square, and then for the odd terms we'll have a minus, and we will have the same a square, but these terms will be 2k plus 1. Sorry, this is minus 2k plus 1, so plus 1/2 will be 2k plus 3/2 square. Is this in the camera? Okay. So now comparing this with the digamma function is not exactly the same, but you can see that that both well, it's not the same because here we have k plus the variable x, k plus the variable y. Here we have a minus and something squared, but we can use this this property like for the two numbers alpha and beta. So alpha squared minus beta squared, the difference of the squares can be written as the sum times the difference, right? And in the denominator, it can be how do you say, it can be changed to partial fractions, and you will get something like this, or you can get like this: 1 over 2 alpha, 1 over beta plus alpha, minus 1 over beta minus alpha. You can see how these partial fractions multiplied by this result in 1 over a squared plus beta squared. So we can just change. You see, we have here beta is a square, and well, no, sorry, we don't have exactly that because this is 2k plus 1/2 squared. This is 2k plus 3/2 squared. But we just expand the squares and then sorry, and then we will get in the end. Let me just give you the results. Yeah, this will be separated into not just sorry, can be separated into each of them can be separated into two partial fractions like this, and there will be a square which will be like the x, and then there will be the okay, etc. Well, in the end, we get that this infinite sum will give you, can be written as the sum of four evaluations of the diagonal function. One at 1/4 minus a over 2. Then another one with a minus sign, evaluated at 1/4 plus a over 2. And then another diagonal function at 3/4 plus a over 2, with a plus sign. And another one with a minus sign again at 3/4 minus a over 2. And as you can see, well, this function is not a simple function, but it can be evaluated similarly to other functions. And this would be the result for this sum for any value of a. If a is an integer, actually it can be done even simpler, because if a is an integer, then maybe we can simplify it more with some of these. Right, if a is an integer, and here we could change these four diagonal functions using the recurrence relation. And then we don't need to evaluate them. Maybe we don't need to evaluate them at very far away points. Okay, let's just finish this with a couple of important values for the record. It's easy to see that from the infinite sum description, it's easy to see that if I evaluate the diagonal function at 1, what do we get? If x is 1, but if this is k plus 1, this is also k plus 1. There is minus, so this would be 0. And then we will get the Euler-Mascheroni constant with a minus sign, okay? Which, remember, is just 0.577, something like that. And if I evaluate the diagonal function at 1/2, well, it has some special value, which I think it's related to series also. Is minus the same Euler-Mascheroni constant minus 2 times the variation. So for these values, this function is negative. Uh, yeah, just remember the gamma function is decreasing between 0. The gamma function decreases from 0 to some value, and then it starts increasing again. And it goes through 1 and 2. At 1 and 2, it has a value of 1. So at 1 is decreasing, and at 1/2 is also decreasing. It has to be negative between 0 and the first minimum. Okay, any question or comment? Not a big expert on gamma functions. So I personally never encountered this function in real life, but it's good to know about it. In the wild, I would say. Well, let's go to one function that really appears a lot. And probably you already know what it is. But let's see this as on the record, the error function, which is used mostly in statistics. Well, it has many applications, but it's mostly used for things related to the normal distribution, because it's defined as the cumulative distribution of the normal distribution. The normal distribution being expressed with the Gaussian function, right? So, as you know, the Gaussian function doesn't have any easy expression for the integrals, for the primitive. So we need to define a special function. It's called the error function, which, well, it's normalized or it's multiplied by 2 over square root of pi to make it have nicer properties, but it's basically the integral from the center of the Gaussian to some value x of a unit Gaussian like this. Okay. Exponential of -3 squared. So yes, this is a very simple function, but there is no simple expression in terms of elementary functions of the integral. So we create our own function, we call it error function, and it's perfectly well defined. We can work with it as we work with a sine or a cosine or any other function, right? It's often also, we often also use, instead of the error function, the complementary error function. And I think the normal way to call it is ERFC. And this is then defined as 1 minus the error function. Okay, so instead of going up, it goes down, but it has the property that is 2 over square root of pi, the integral from x to infinity of the Gaussian. So now you can see why the 2 over square root of pi is this. Of course, 2 over square root of pi is the total area of this Gaussian from minus infinity to infinity. So that means the error function grows from -1 to 1. And this, you plot these, and you plot this in Wolfram alpha, whatever, and you can see how the error function starts when x is negative, it starts very close to 1, to -1. So it has this asymptote at -1, then it just goes to 0, and then it goes asymptotically to 1. is a type of sigmoid, right? Sigmoid functions which are always the same like an S, and it's very common. The complementary, so this is the function. The complementary function, as you can see, is just 1 minus this. So when x is negative, it actually starts at 2. 7, 2, 9, or b. So it starts at 2. This is 1, this is 2. And then when the error function goes to 1, this function goes to 0, right? And when the error function is 0, the complementary is 1. So it looks a bit like this. 1, and then it goes to 0. Actually, it goes quite fast to 0. This is a complementary error function. Okay. What can we say about these functions? Well, there are some properties that they can mention. Of course, the error function is you can easily see it's an odd function, right? So the error function of minus x is just minus the error function x. It's an odd function. And from the integral, you can see it because the Gaussian is with respect to 0, so there are x equal minus t, for example. Then you will get the same one. The error function has a Taylor series that sometimes can be useful. So let me mention it here. The 2 over square root of pi are outside of the sum, and the Taylor series has these coefficients are minus the n divided by 2n plus 1 plus factorial of n, and then the powers of x to the 2n plus 1, which is not surprising because it has only odd powers of x because it's an odd function. I think that will always be the case. So this function can be easily get from writing here the expansion of the exponential and integrating term by term, and you can get all these numbers from the Taylor series of the exponential. The error function also has an interesting asymptotic behavior, which is a little bit easier to see for the complementary error function. For large x, you see the complementary error function looks a bit like the exponential of negative x, right? So it's that kind of decrease. Actually, it's a bit different, but similar. So for large x, the complementary error function becomes closer and closer to the exponential of minus x squared divided by the square root of pi and divided by x. So it's like Gaussian divided by x. And to write this limit, we can say that for large x, the complementary error function will be this function multiplied by 1 plus a very small number, a number that decreases as 1 over x squared. Okay. So this is a way to tell the for For small x, there is not a big mystery because we have the Taylor series. What is the derivative of the error function? What is the derivative of the error function? You can have a very good guess of the definition. What do you think? What do you think is the derivative of the error function? Okay. The error function is defined as the integral of the Gaussian. Then the derivative of the error function is the Gaussian. Okay. So the error function is the integral of this. That means the derivative of this is something like this. Okay, you can see the derivative of the error function is, well, yeah, exactly 2 over square root of pi the exponential of minus x squared. Okay, the Gaussian curve. Well, actually, this is the same definition. You can define the error function like this: a function that has the derivative equal to that normalized Gaussian. It's normalized to have a total area of 1, or no, of 2. Sorry, a total area of 2, or a total half area of 1, so that the error function goes to 1. But yeah, just by this definition, we just say integrate from 0 to x, and that is the value of the error function. Okay. The integral is not, the integral of the error function doesn't require another special function to be defined, because in general, for like the primitive for any limits, if I integrate the error function with respect to x, I just get x multiplied by the error function plus the exponential of minus x squared divided by the constant square root of pi. So I get a function that can be expressed in terms of functions that we already have. Anyway, the integral of the error function is not as interesting. The error function itself, as I said, is very interesting because it tells me the distribution of probabilities for differential distribution that has the shape of a Gaussian, which is like the most common probability distribution in physics, right? Because it happens whenever you have a lot of events that follow a simpler binomial distribution, for example, then you will always get a Gaussian. So that's why in quantum mechanics or wherever you use some statistical mechanics, etc., it will be like the simple case, the Gaussian, and the integral of probability density function is a cumulative probability, and for the Gaussian we need to use the error function. Well, let me remind you here of some specific values. So as I was trying to show you in the graph, the error function of 0 is 0. The error function when x goes to infinity is 1. And the error function when x goes to minus infinity is -1. And from the same definition, the complementary error function 0 is 1. The complementary error function at infinity is 0. And the complementary error function at minus infinity is 2. So a function with a lot of applications, not so exciting. No, I think it's not a super interesting function, but it has it appears a lot, and it's a very practical thing that you can see in a lot of problems of statistics. Let's go for something a little bit less usual, but I think it's fun. Probably you have heard of the zeta function. The full name is the Riemann zeta function. And it's called the it's called the zeta function from the letter that we use to describe it. How do we write the Greek letter zeta? I think you have used it in other courses, right? For the zeta function, sorry, for the letter zeta, we just start with like a tau and make it longer, something like this. It's like a straight Z, if you want. So the Riemann zeta function, in most sources that I know, is often written as function of a complex variable S. I guess I'm not sure exactly why, or maybe because the zeta is like a Z, we don't want to use Z. But if we write S, it's also kind of telling you that we want to explore all the complex values. Whereas for a function like this, well, the error function is actually not defined for a complex number because this is a line integral of the real axis. There is no definition of the error function from this definition. We cannot take it evaluate a complex variable. I guess there will be some analytic continuation, but again, if some function is not really useful for us, then probably we don't need to think much about that. And the error function, as I said, is interesting for probability distributions mostly for us. So remember that I told you that the sum from n equal 1 to infinity of 1 over n divergence, right? I told you several times, but I mean, it's an interesting mathematical thing. And as I was mentioning before, we can calculate something like 1 over n squared using some methods. For example, the contour method that we discussed in the previous class, the class before the previous class. And if in this case, this is the example that we did, right? In this case, we can use the contour integration. Remember to go from minus infinity to infinity, and noticing that minus n squared is the same as n squared, then we see that we can separate it into 3 pieces until -1. The 0, then we skip it because it's the pole of the function, and then from 1 to infinity. These two parts are equal, so we can just calculate that and divide by 2. Now the problem is, so we can also do that for n to the 4th, n to the 6th, etc. The problem, if this is not an even number, or even if it's not an integer, or even if it's not a real number, imagine it's just any complex number S, then this sum, well, the sum from minus infinity to infinity could be calculated with the contour integral, but the sum from 1 to infinity cannot be deduced from that, because the two parts, the negative n or the negative n and the positive n, will not be related in general. So we can calculate the total from minus infinity to infinity using the contour, but I cannot separate it into negative n and positive n. And actually, this problem becomes, well, something that is well defined. I mean, the value of this sum exists and is unique as long as S has a real part larger than 1. Remember, if S is real, I told you 1 over n to the power of 1 diverges, but any power a little bit larger than 1 converges. And if S is complex, actually, the imaginary part only creates some kind of phase. So the important thing is the real part. The real part needs to be strictly larger than 1. And for 1, it doesn't converge, or for negative, for negative real part, or anything less than 1 will diverge, because this thing will either increase or decrease too slowly. So this is the definition of the zeta function. It's just that the zeta function evaluated at S. You see here, you calculate the sum for each value of S, and it gives you a nice analytic function that is exists for all the infinite half plane with real part larger than 1. However, it can be, since the function is analytic and it's defined on a B, sorry, what I was saying, on a B domain, analytic continuation can be used to define it for other values of S that don't have real part larger than 1. The only point where the function doesn't exist is at S equal 1. So here it can be, remember analytic continuation, which the method is a lot, but let's say we can define a Riemann zeta function that is exactly like this in the half plane part real part of S larger than 1, and that it exists in the other parts of the complex plane. So let me see. So we can continue to all the complex values except the value S equal 1. Not surprising, because we know at S a little bit less than 1, these things converge slowly, and if you go to S equal 1, this is not going to be analytic, but it's actually a simple pole. So not a big deal, right? There is a simple pole at S equals 1, but it can be defined for every other point. Also, you can see that if S is real, then the larger and larger values of S will make these numbers smaller and smaller. The sum will also be smaller. And you can see how it increases monotonically for real S. Okay, it's a function that increases with S or real S, or S larger than 1. Right here, monotonically decreasing for S larger than 1. Should I say increasing S like anything else? So if S is real, okay. Another property of the zeta function is that even if it looks completely disconnected, we can also define the Riemann zeta function as an infinite product. The infinite product, instead of an infinite sum, we have an infinite product of factors of this form. 1 divided by 1 minus the number p to the power of minus s. But now, the values of p are the prime numbers, which is quite amazing. So the same function can be expressed like that, where p are all the prime numbers, okay? How can we put here all the prime numbers? The prime numbers can be super large, but okay, notice if you have here a prime number that is super large, and the real part of s is larger than 1, then we will have a negative power that will be super small, and then you will be multiplying by 1, basically infinite. There will be infinite terms that we multiply by 1. So a infinite product like this will probably converge for just some number of primes. What else I wanted to tell you? Is zeta function. There was something very interesting about this zeta function that okay. If you have some experience with one of the special functions, I will also like you to share. Remember this. In this course, we like to talk about maths, but we also like to talk about applications in physics. And well, many of these functions would appear if you do theoretical work, but not all of them. Many that appear when you learn quantum or when you do statistics. Or I will show you in the next topic. I will give you a couple of examples of basic physics that requires special functions if you want to study properly, not like we teach it to the young students. Okay, for the zeta function, let's take a look at some of the values. If I try to evaluate the zeta function at 1, of course I cannot. Let me write it like this. I mean, you could write it like this if you include remember the extended complex plane with the infinity, with the point at infinity, then we could write the zeta 1 is the point at infinity. That will be correct in that sense. If I evaluated at 2, then we calculated this value, remember, with the contour method. And remember, we got pi squared of 6. Okay, so from 1 to 2, it decreases from infinity to pi squared by 6. And also, we know the value at 4 because it can also be calculated from the contour method. Remember, for all the even integers, these values are easy to calculate from the other method. This will be pi over 4, pi to the power of 4 over 90, etc. And before we take the break, let me just mention the related Hurwitz zeta function. The Hurwitz zeta function is normally expressed again with the letter zeta, but with two variables, s and a, for example. And this is a generalization of the Riemann zeta function, in which you add, well, here you start from 0, but let's see why. You start from 0 instead of 1, and then instead of taking the power of n, you take the power of n plus its constant, a. Well, it's a constant in the sum, but it becomes another variable of the function. So changing a will also change the value of the function. And this would converge again for any S with real part larger than 1, no matter what A is. The only problem here is that if A is negative, for example, imagine A is -4, then there will be a term that diverges. When L is 4, it will be 1 divided by 0, right? So we have to include an exception for that. So let me write it here, where any term that has n plus a equal to 0 is omitted. Okay, so we don't want to add an infinity to the function. So if n plus a is 0, then that term is not included. So as you can see, the Riemann zeta function is the special case where a is 0, right? And this one starts at 1, but this is just because we are skipping the term n equals 0 and starting at n equal 1. But it's a special case of this for this zeta function. Okay, so let me write it here. So the Riemann zeta function is the Hurwitz zeta function at 0. Actually, that's not in the notes, but it's clear, right? If a equals 0. But another thing that is interesting is that the Hurwitz, I'm not sure how to write it. The Hurwitz zeta function at 1 is also here. Yeah, 1 it is also the Riemann zeta function. Sorry. Well, I mean at 0 it will also be, right? It's at a equals 0. So if a is equals to 0, you have 1 over n to the s, and you omit the term n equals 0. If a is equal to 1, then you have 1 over n plus 1 over s, and that is, you can write directly like that. N plus 1 starting at 0 is the same as another n starting at 1, right? So you can also see that for a equals 0 and a equals 1, the Riemann zeta function is recovered. Should we take a break? Let's continue. The next family of functions that I want to talk about are called elliptic integrals. And we can call them elliptic integrals just like that. Or if you want to be more specific or like longer names, these are also called Legendre's elliptic integrals. Okay. And these integrals appear for the first time when people try to write expressions for the length of an arc of ellipse as a function of the angle, which is useful for astronomy, for example, for the calculation of orbits and things like that. But actually, they have other applications that I want to mention. But yeah, that's why they call elliptic integrals, because they are based a bit indirectly from the definition, but you will see. They are based on how long one piece of ellipse is, depending on the axis, the major axis. But okay, the definition you don't see explicitly. Let me start by introducing. There are like 4 types of elliptic integrals. So the names, normally we use the letter to represent the elliptic integral, and that is normally everyone agrees on the names normally, but let's talk about the names. The two first functions that I'm going to talk about are called complete elliptic integrals, and they are called the complete elliptic integral of the first kind and the complete elliptic integral of the second kind. So I will call this K, and for traditional reasons, the variable is going to be N. And of the second kind would be called E. Now, N can be, the functions can be evaluated at a general range of N, but the range of interest is going to be between 0 and 1. So just keep in mind, let me write it here. Usually, N is between 0 and 1, but it doesn't need to be, okay? But this is the case where the elliptic functions have more, sorry, elliptic integrals are mostly used. So they are defined as the integral from 0 to pi over 2 of 1 divided the square root of 1 minus m sine squared theta. And as you see, it's a very innocent looking integral. It looks like an easy integral, but it's not. If you try to solve these in terms of elementary functions, there is no expression of the result for a general value of n. Only for specific values of n, it will have some easy value, or that means a value that is easy to calculate. For example, for n equals 0, it's trivial, right? And for n equal 1 is sorry, actually for n equal 1, this would diverge, so it's not a good example. The second kind, maybe is a better example. The second kind is the same, but it has the square root in the numerator. Okay, so it has square root of 1 minus m sine squared theta, just integrated from this extreme 0 to pi over 2. As you may guess, this interval that is fixed is what makes these functions complete. And like for the gamma functions, the usual function is the complete function, and then we can define an incomplete gamma function by putting another variable from the limits. For the elliptic integrals, is a bit the other way around. The normal, let's say the most used function is the incomplete function, so we don't call it incomplete. We will call it just elliptic integrals. And when we integrate over the full range from 0 to pi over 2, we will specify that these are complete. Anyway, this is just the name. As I said, again, this looks like an easy function, and you can think of how it looks. I mean, just imagine a real number m that is between 0 and 1, just to make things easier, because if m is larger than 1, here we will have a complex result, right? Because we have the square root of a negative number. But if m is between 0 and 1, then the function is easy to imagine, and the integral of that is also kind of simple. Actually, negative m is also interesting. So maybe let's just specify that m should be less than. But I will see that I will show you that for negative m, the functions are have some symmetries. So normally it's the interval of interest is from 0 to 1, but it could be less than 1. You see, if m is less than 0, then here there is no problem either. Yes, the integral of the square root of a positive number. Anyway, these functions actually can be plotted easily, but they look a bit boring. I don't know. So if I plot them from 0 to 1, both of them start at the same point, which is pi over 2. As you can guess from the, as I said, the trivial result at n equals 0 for both of them is just the integral of differential theta. So the integral of differential theta between 0 and pi over 2, which is pi over 2. And both of them are quite flat. But E decreases slowly from pi over 2 to a smaller value. What value? What value? What? I think it's 1. Yeah. Yeah, this decreases to 1. So if this is about 1.5, it decreases to about 1, so a little bit more. It's a very small and simple function that decreases very slowly from pi over 2 to 1. And this is E. And K increases also very slowly at first, also very flat, but when it gets very close to 1, it jumps to infinity. Okay. Only for values very close to 1, it goes to infinity. Otherwise, the values that these two functions take look very simple, but they are expressed as this special one. And now, to relate it with the original problem that mathematicians at that time were facing, for example, one application of these elliptic integrals is that if you calculate the total length of the arc of an ellipse, or you can call it the perimeter of an ellipse, with semi-major axis A and semi-minor axis B, okay. Ellipse, this is A, this is B, and you want to know the length of the curve, the total length of the ellipse can be calculated as 4 times A, the complete elliptic integral of the second time evaluated at 1 minus B squared over A squared. Okay. Which includes, of course, the case of the circle. Remember, the circle is just an ellipse where A is equal to B. If A is equal to B, here we have the value at 0, which is pi over 2. So we have 2 pi A, which is the length of the circle, the triangles. Okay, easy, right? The two definitions can also be changed in a way that they look exactly the same, but with a cosine instead of a sin. And that is that can be useful sometimes. So if I change the sign with a cosine, I get the same function. And to understand that, you just need to notice that we are integrating from 0 to pi over 2. So I can change from theta, we can change from theta to pi over 2 minus theta, and then the sign becomes a cosine, and the limits are changed, but there is a minus in the differential of theta, so you get the same equation with a cosine. Okay. But there are other definitions that can be useful that look quite different. This is an alternative definition. Another alternative definition is the integral from 0 to 1. Now let's change from theta to x. 1 divided by the square root of 1 minus x squared times 1 minus mx squared. Okay. This is doing the change of variable x equals sine theta. You can change the sine squared to x squared, and the differential of x will have a cosine that is 1 minus x squared. And yeah, you can get this expression for k, and similarly for e, I can get the integral from 0 to 1 of, in this case, we have the square root of 1 minus mx squared in the numerator and 1 minus x squared in the denominator. Which is, again, these functions are quite simple, but the integrals are the elliptic integrals. Well, sorry, let me write this here. I apologize for using only one. Anyway, I'm going to show you these notes because I think it's would be easier just to have them. Now, another thing that you can calculate or you can express in terms of complete elliptic integrals is a similar integral, but with just a sine or a cosine instead of a sine square or a cosine square. Well, let's do it for a cosine. The integral now from 0 to pi instead of pi over half. Let me change from theta to another angle just to show the change of variables. If I have a constant b that is larger than 1, plus or minus the cosine of pi, not square now. So this very simple expression, again, we cannot write it in terms of all the functions, but it can be expressed in terms of the k function. Here, as 2 over square root of b plus 1 times the function k evaluated at 2 divided by b plus 1. And similarly for the square root in the numerator, see integral from 0 to pi of the square root of b plus or minus the cosine of angle pi is 2 square root of b plus 1 times e evaluated at 2 over b plus 1. So you see, these integrals may appear in other topics, but they could be useful for this case. If you want to know where it comes from, you just need to use the The equations for the double angle, okay? Just define phi to be 2 times theta, remembering that the cosine of 2 times theta is related to the sine square of theta or the cosine square of theta, and there are two expressions for that. And then you can find these expressions. Okay. So the basic things. The we don't need these definitions again. Okay, let me keep this for the moment. And if you don't mind, I will use this corner. So, as I said, between 0 and 1 is the places where we normally are interested. But n could be negative. If I want to see the values of the functions between -1 and 0, let me write here. So if m is larger than -1, you can see that k evaluated at -m is related by the product 1 over square root of 1 plus m to k evaluated at m divided by 1 plus m. Actually, this is true for negative or positive m, as long as it's between -1 and 1. And for e, we will have e of -m equal the square root of 1 plus m times e evaluated at that m over 1 plus m. Okay. This can be done from the definition. The derivatives of the elliptic integrals are also expressed, we can express them as elliptic integrals. The derivative of k, let me start with the derivative of e. The derivative of e with respect to n is e of m divided by 2m minus k of m divided by 2m. The derivative and again, well, if you want to find this case, then you also can use the trick of introducing a b, like I was telling you for the other problem. You could come here, introduce instead of this one, and write the general of this function b minus sine squared theta, which will include the case b equal 1. But when you put here a b, you can differentiate under the integral sign and find an expression for the derivative of that function of m and b, and then evaluate it at b equal 1. And then you get this. For k, similarly, we have the derivative of k is e of m divided by 2 times 1 minus m times m minus k of m divided by 2m. As I said, there are some special values that are fine. At 0, both k and e are equal to pi over 2. Remember that m equals 0 is also related to the limit of an ellipse with 0 eccentricity, so it becomes a circle. And as I was telling you, when n goes to 1 from the left, k diverges, but e doesn't diverge, and e of 1 is 1. Yeah, so it's easy to see from any of these equations. For example, here, if n is 1, you have 1 minus n squared, which is the cosine squared, and the square root of the cosine squared. So it's the integral of the cosine. The integral of the cosine between 0 and pi over 2 is 1. So that was easy to see. Okay. Now, before we continue, I would like to mention something that is not in the notes, but that I think as physicists, we will find interesting, right? So, I mean, it's not something that you need to know, but it's good to know. One thing, what is the electric field or the electric potential created by a ring? You learned that since you were small kids in college, right? You learned that as bachelor in your years of bachelor degree. If you have, imagine I have a charge ring. I have a charge ring on the XY plane, right? This is the z-axis. And I want to find the electric potential created by the charge ring. If you try to remember when you learned about this, probably you will remember that normally the teacher will tell you how to find the potential on the z-axis. The integral is much easier, so of course, if you want to find the potential on a point of the z-axis, then you can just integrate for each element of length. Well, let's assume the charge on the ring is uniform. It has linear charge density that I'm going to call lambda, charge per unit length. And then you take an element differential of length, and you can calculate the distance, right? You can calculate the distance. The potential is just the some constant times the integral along the ring of the charge density multiplied by the element of length divided by that distance, right? And if you are on the z-axis, that distance is constant. Well, the distance is the constant along the ring. So you can take it out of the integral, and you just need to calculate that distance set. It's like easy. Okay? But what happens if we are, for example, here? What happens if we are here? The distance now is a function of the position of the L. So even if lambda is constant, R is not constant. Okay, so I'm not going to solve it. I mean, we could solve it step by step, but I just want to tell you that the result of this problem as a function of the of course, in the case when you are on the axis, what are the important parameters? What is the radius of the ring, the linear charge density, and we can also take the value of z of interest, right? The value of z. Okay. And also, if you are if you are not on the z-axis, there will be also the minimum distance to the z-axis, which is the cylindrical coordinate rho, right, of the point. This is here. This is just any point in space. This is R. This is rho. So the result for the general case that includes the case when rho is 0 is that the potential is lambda over 2 pi epsilon naught. The radius of the ring divided by 2 times that polar cylindrical coordinate to the 1/2 times the square root of 2 times some variable m multiplied by the elliptic integral of the first time k evaluated at m, where m depends on the radius of the ring, the polar coordinate of the points, and the vertical distance, like this. 4a rho divided by z squared plus a plus rho squared, which could be less than 1, right? Otherwise, a diverges. Is this less than 1? So here, notice a plus rho will be this plus the radius, and then we do right triangle. I'm not really sure. Anyway, this is the result that you get, and let's see. And it includes to get the case rho equals 0, then we just need to take a limit for it, because notice when rho is 0, we will have a here in the denominator. Okay. I think it's correct. Another example that I want to mention, I mean, this is just a comment that, of course, in the undergraduate program, you don't need to know about the elliptic integrals, so there is no closed expression for the potential at random point in space. But if you know about the complete integrals, similarly, there is a very basic undergraduate problem, which is the pendulum. And you know that the pendulum problem it's one of the most basic problems. And the evolution with respect to time of the angle of a pendulum, I like here the force of gravity, the tension of the string, blah blah, and the equation of motion follows this differential equation. Second derivative of theta with respect to time plus acceleration of gravity divided by the length of the pendulum L times sine of theta equals to 0. The sine of theta comes from the projection of gravity in the direction of the length. And then your teacher will say, well, but the angle is very small, right? The angle is very small, so the angle and the sine of the angle are the same. Sure, okay. If you don't do that, then you get stuck. But actually, this can be written with the elliptic integral k. So let me give you the result. So the result that we know, for example, the period of the pendulum, which first the small angle case is more interesting because the period of the pendulum doesn't depend on the amplitude, right? So for small oscillations, the period will be the same no matter where you start exactly. So that means, let's say, if the amplitude or the maximum angle, we call it plus 0, is really, really small, then the period, we call it the period for the case of small angle can be easily written as 2 pi square root of L over G. But otherwise, if the amplitude is not very small, then the period depends on the amplitude. And the period depends on the amplitude like this. 4 square root of L over G, the function K evaluated by the sine of amplitude divided by okay. Which you can see if the angle is very small, that means the sine is also a very small number, then you will be in the region around here, and the values will be very close to pi over 2. Then you will have pi over 2 multiplied by 4, which is 2 pi, right? Times square root of L over T. Okay, just a couple of examples to show you that if you want, you can use elliptic integrals as a physicist. They are not, well, they are a bit old-fashioned, but they are still interesting for this type of calculations. And of course, the small angle of estimation is still good. You see how flat this function is. It only becomes large when the sine of theta 0 over 2 gets close to 1, in which case it diverges. But that will be the case of a pendulum that is exactly upwards in unstable equilibrium, and the period will be infinity. But if you just move it a little bit, then the period is larger because of the minutes. And this equation will only be true if the string is rigid, not just a tension string, but more like a, what do you call it? Like a bar. Okay. Any question about elliptic function, elliptic integrals? Well, I still have other elliptic integrals that I'm going to kind of overwrite here because they are very similar. Maybe let's use red so you can notice. That's, oh no, now I have to find red. So if I make this integral incomplete, then I will need to add another value to these functions. Okay, and for some reasons, instead of writing this with a comma, I'm going to just show you the normal way to do this. The elliptic integral of the first kind, as I say, we don't say incomplete, we just say elliptic integrals. And you can understand this. They are not the complete elliptic integrals, or you can just notice that they have 2 variables instead of 1. But the k becomes n, and then we have some angle phi and some value of n. But as I said, separating them like this, it's common to write them in these formats. This just with a vertical bar. The definition is the same, but you go from 0 to some angle that can be different from pi over 2. Okay. For the second kind, the elliptic integral of the second kind, actually we use E again. But again, it's normally clear from the context, basically from the number of variables, if this is the complete or incomplete elliptic integral. Like this, right? Let me continue the loop. So of course, it's easy to see from the two definitions that the complete elliptic integral is just a special case of the elliptic integral when this is pi over 2, right? And the same for E. E of M is just E of pi over 2 N. Sorry, vertical bar. What else? Actually, there is a symmetry in these integrals that makes the function it's not necessarily a periodicity, but it has some translational properties in which if you add an integer number of pi radians to phi, or you do n pi minus phi, in both cases, the function f would be the same as 2 multiplied by n multiplied by the complete elliptical integral for that value of n plus or minus the value of f at phi. Okay, so like jumping from one value of phi to a value of multiple of pi plus phi, for example, you just get this plus a multiple of the complete integral. And you can see from the periodicity of the function of the elliptic. There is a similar expression. Let me give you the expression for E. N times pi plus or minus pi and some value of n is equal to 2 times n times E of n plus or minus E phi slash n. Okay. So here n is any integer. Now, I have another important family of elliptic functions, which again, they're maybe not so useful, but I think they're quite funny to learn about. So to introduce the other family of elliptic functions, let's define the inverse of f. The inverse function of the function f, which is called the amplitude. So it's the inverse with respect to the angle. Okay? The inverse of m is of the amplitude. And you can also notice that in all of these equations, we normally treat m as something constant. So that's why I think that's why we separate the variables in a way that then we can see that they are treated differently. Normally, the angle is something that is more treated like a variable, like something that we want to change and see what happens. And normally, n is just a parameter of the problem that is fixed. Really, in this example, like okay. Again, we can imagine that we are interested on the dependence phi for the elliptic integrals that are not complete. So how do we invert these functions? Well, we just need to find an angle phi that we call the amplitude of a variable u at some value of m, such that if phi is this function of u, then u is the elliptic integral of phi for that value of n of the first kind. Okay. So we define the amplitude by inverting that. And this function is, so how do we interpret this function? Look, just notice this function is always going to be an angle, right? It's an angle, and it has as a variable what would be the output of this function, which is not necessarily an angle. So it's some kind of converting from a variable that will have some limits that we can see to an angle that will normally be between 0 and pi over 2. But it doesn't need to. As we have seen, you can go out of that interval with these expressions. Anyway, what is, for example, what is the amplitude? What is the amplitude? Sorry. What is the amplitude of some number u at n equals 0? Okay, let's see. The meaning in the limit case. Remember, in the limit case, when n is 0 is where these integrals become just the integral of pi, right? When n is 0, we just have the integral from 0 to pi depends on theta. So it's just theta between 0 and pi, which is pi. So in the case n equals 0, this function is just pi. So what value of pi returns pi? Sorry, what am I saying? Okay, so we need to find an angle that, if we put it here, returns pi. Sorry. If m is 0, right? So yes, it's just the same number. Okay, so for m equals 0, the amplitude is just the linear function. Amplitude of u equal u, it's just a straight line. Also, another thing, if m is not 0, but I evaluate the amplitude, no, if I evaluate phi, sorry, if I evaluate f, who's calling me? If I evaluate f at phi equals 0, then to see the integral from 0 to 0 is 0. So at phi equals 0, if phi equals 0, then f 0. At phi equal pi over 2, then f is k, right? So how can we use that in the inverse? So the inverse will say, what is the value of phi that, well, it's just going backwards. Okay. What value of phi makes f equal 0? So the answer is 0. What value of phi makes f equal k? And then the answer is pi over 2. So that means the amplitude, well, this is the amplitude of 0, the amplitude of 0 is just 0. The amplitude of K of m is pi over 2, right? And in general, we can also think about what happens if I jump for another value of x. Okay, these two cases can be extrapolated using this. You just get this expression. The amplitude of any integer multiple of k of n is just the same multiple of pi over 2. This includes the case of 0. Okay. This is for any integer. Okay, so as I was saying, introducing the amplitude as some kind of angle related to another variable u, there is a new family of functions that can be constructed. I'm going to erase this. Now, I'm going to keep the name elliptic because these functions are also related to the elliptic integrals, but they are called just elliptic functions. And if this sounds ambiguous, you can add the word Jacobi, Jacobi's elliptic functions, to specify what we mean. Jacobi's elliptic functions are, on the one hand, an extension of the trigonometric functions. So trigonometric functions will be a special case of these elliptic functions, the same as the circle is a special case of an ellipse with 0 eccentricity. I mean, the elliptic functions are much more complicated than the sine and the cosine. Well, not much, a little bit more complicated, but as I said, they include the sine and the cosine, and a bit more surprisingly, they also include the hyperbolic sign from the hyperbolic functions. So they are. I never found them in any program that I work with, but they are interesting from my point of view because is this double generalization. It generalizes both trigonometric and hyperbolic functions to something in between, or something that includes all facilities. Remember, we one property that I can mention now, but I'm going to show you why, is that if you remember, the trigonometric functions have a period along the real axis. The hyperbolic functions have period along the imaginary axis. These functions will have double periods, and they make them interesting because if you know the values in just one rectangle of the complex plane, then in every direction you can just repeat that rectangle, you get the same value. So you have double periodicity, which is not a very common thing. We haven't seen any example of a complex variable function that has periods both in the real direction and the imaginary direction, right? Can you think of any? We haven't seen any. So, okay, but let me define it. I'm going to define two of them. There is the two very simple functions, and now these are not functions of an angle. These are functions for a general variable. I'm going to call it x, like in the notes. We can see that this can be generalized to complex plane. So if I fix n to be some value less than 1, then the function Sn is just defined to be the sine of that function evaluated at x, the amplitude. Remember, the amplitude is an angle. So I can take the sine of the amplitude and I get a function of x, which is related to the sine of x, but it's not the sine of x. Well, it would be only the sine of x in the case where the amplitude is equal to the amplitude of x equal to x, which is only for n equals 0. So yeah, for n equals 0, the the function Sn becomes just the sign of x. And similarly, we can define an angle function Cn of x to be the cosine of the amplitude of x. As I say, normally just we want to see what happens when x changes. So let's imagine m is just a fixed value, but of course, these things depend on m in an interesting way too. But okay, in my view, m is more like the variable that tells you what function of the family you are talking about, and x is the variable of the function that really the thing that you plot, per se. Well, I'm sorry. Okay, so far so good, right? How do we call this function? So that is the funny thing. This Sn is, some people call it the snine of x. And the Cn would be the knine of x. But it's a bit difficult to pronounce. So it's just following the sine and cosine. So this could be called the snine and the knine. Let's talk a bit more about these two functions. Remember, this is a reminder. You remember this? The inverse of the sine, the arc sine, is related to this integral. Do you remember this? Okay. The arc sine can be defined as the integral of 1 over square root of 1 minus y whole square. So in the same way, we can define the inverse of the sine, again for some value of n, to be the integral between 0 and x of, and here we have similarly a square root, but we have a product of 1 minus y squared and 1 minus my squared, which looks similar to what we have seen before. This is the inverse of the sine. And again, you can see how when n is 0, you just recover the definition of the arcs. So this is the arc sine, and the arc line, the inverse of the Cn function, will also have some expression in this case. It can be expressed as the integral from x to 1 of actually the same sorry, the square root, and here we have 1 minus y squared multiplied by 1 minus m plus my squared. Okay. But again, when n equals 0, this becomes the complement of this integral. Anyway, there is a third. So these are the two basic elliptic functions, sine and nine. Their inverse, the arc sine, arc nine. There is a third elliptic function that is simpler, that is called the nine, the n. This function can be defined as just the square root of 1 minus m multiply the 9 squared x. So we can just define it like this. So notice when n goes to 0, this just becomes constant, equal to 1. Okay, but there are more. How many more are there? Do you know? There are 9 more. So there are 12 in total. But they are not so difficult to define. I mean, in trigonometric functions, you define this 100%. And all the other things are just combinations, right? You have 1 divided by the sine, the cosecant, 1 divided by the cosine, which is the secant, sine divided by the cosine, which is the tangent, cosine divided by the sine, which is the whole tangent, and then the inverse function, right? Sorry, in the 12, I'm not including the inverse functions, only the direct function. So when in the trigonometric case, as you see, we have 6. So here we have only a few more. But instead of giving you all the list, let me write the symbol PQ, a function PQ, but here P and Q are each of them either S, C, D, or M. Okay. So for example, Sn is the one with P is S and Q is N. Yeah, and P is V and Q is, right? So any combination, that's why these functions have these letters, because the names are related to the properties. So the names always have these 2 letters that here are going to be P and Q, and they have the property that for any combination, PQ is always equal to P, another letter R, divided by Q and the same letter R. And this is true for any R that you choose again. Example, if I have Sn divided by Cn, the sine divided by the 9, then here is like the R, like the N cancels, and then you will have some function called Sc, right? Just a combination of letters. So, as I said, in trigonometry, you can define all the secant, cosecant, tangent from only the sine and the cosine. The elliptic functions can also all be defined from the sine, canine, the 9, and maybe the in 9 or the sine. But okay, if the letter is repeated, we don't need to define a function, because if the letter is repeated, then of course the function is just 1. For example, SS will be SR divided by SR, which R can be anything like M. So SS will be Sn divided by Sn, which is 1. CC will also be Cn divided by Cn, which is 1. So a repeated letter is not interesting because that's a constant 1 for any value n. Okay. Let me write here. But the SS, the CC, the DD, and the NN are just the constant function 1. But yeah, the other functions are just can be defined with divisions like that. And if you want to, if you change the order of the letters, ND, the XN, then you can use this expression if you want. But notice that if I use this expression and write here N, and here I write E, and then if I choose R to be also N, then the numerator is 1. So changing the order of the letters is always 1 divided by the order of the letter. Okay, so ND is 1 divided by the N, and S is 1 divided by Xn to be. So this function takes the limit to this. So NS will take the limit of the cosecant, right? Things like that. Anyway, I have a plot here. It's difficult to show. I can try, but first first let me try. So already, maybe I should keep the definition of the amplitude because all of these things are related to the trigonometric functions of the amplitude. Okay, let me see. Let me show you what happens if I plot the three basic functions Sn, Cn, and Dn. Well, they will depend on the value of m. So if I choose a value of m, for example, in this plot, I will show you. I think I will send you these notes, right? So you can see it also. For example, if we take m equals 0.8, then what happens? If m is 0.8, well, here we don't see it, but the period of this, the amplitude becomes something that depends on the function f. Anyway, the thing is that the amplitude of x will will change by a difference of 2 pi after x goes through some other period that depends on m. Actually, it depends on k of m. The period here, see, the period will be 4 times the value of k the value of k for that. Oh, it's here. Yeah, it's here. So here you can see how when the variable u, here I'm using it as x. So when the variable x changes by a multiple of this number, the function k evaluated at m, then the amplitude changes by a multiple of pi over 2. So the periodicity, one period of the amplitude, 2 pi of the amplitude will be when this is 4. That means 4 times the value of function k, which remember I told you it's something like this that diverges near 1. And so the periodicity of these functions are longer for m close to 1. For m equals 0.8, for example, well, it would be, I don't know, yeah, something larger than 2 pi. Let's write it like, so here, this value will be 4 times k of 0.8, whatever it is. So from 0 to this value, there will be 1 period. The S9 looks a bit like the sign, and of course, for real values, the S9 goes from -1 to 1 because it's just the sign, right? So this will have a maximum of 1, a minimum of -1, and it will look more or less like the sign, but the maximum looks a bit more rounded, and the minimum also looks a bit more rounded. The 9 looks a bit like the cosine. Oh, well, and this will be an odd function. Okay, this will be an odd function, like the sine, because the amplitude, well, for whatever reason, the 9 it will be an even function, similarly to the cosine, but the maximum is sharper, and then another difference is that it has some inflection points for this value of m. For this value of m, I have one more assignment that I may give you to explore the inflection points. Inflection points means the curve. So the curve goes from 1 here to -1 here, the same point as the 0 of this line, but it doesn't. Normally the cosine changes from concave to convex only once, and this changes 3 times. Okay, it goes like this, then like this, and like this. We didn't put it very well, but it has a little bit of change in the. I don't know how to plug it better. Anyway, for this value of m, the 9 changes the second derivative. The sign of the second derivative changes 3 times instead of 1. The d9 is actually something. The d9 has actually double the period. It has a maximum here and another maximum here. with the same value, and then it's periodic like this. Okay. And depending on the value of m, all these things will change. But if you go in the limit when m is 0, then the S9 should become a sine, the K9 should become a cosine, and the D9 should become just the number 1. Okay. Because you see, when m equals 0, it's just the square root of 1. Okay, let me give you just a couple of properties that we want to remember about these functions. As I said, they have a trigonometric limit when n goes to 0. So when n is 0, all the elliptic functions become some trigonometric function, or the constant function 1. So, as I told you, the S9 of x0 is just a sine of x. The K9 of x0 is the cosine of x. The D9 of x0 is just a constant number 1. And any other combination will also become a trigonometric function. For example, the ns will become the second, the nc become the second, and the Sn divided by Cn will become the tangent, etc. Now, what is a little bit more unexpected is the hyperbolic limit. Now, if we still look at the real axis, then there is something that doesn't match, right? The trigonometric functions are not periodic in the real axis, and these elliptic functions are periodic. But notice that the period depends on the value of k for m, and k diverges. So the period of these functions becomes infinite when m goes to 1. And in that case, when m is equal to 1, all these functions that look periodic for m equals 0.8 become not periodic, or let's say we have an infinite period, which is the same as saying, yeah, periodic. And now the names don't really match, but you can see how the S9 of x when m is equal to 1 is exactly the hyperbolic tangent. And the K9 of x when m is 1 comes also the D9, both the K9 and the D9 of x when n is 1 becomes the hyperbolic second. And again, the other possible elliptic functions will also become some hyperbolic function. Other property that is quite simple is just from the definition of the sine and the K9. You can see that for any value of x, we just write it just without the x, and for any value of x, the S9 squared plus the K9 squared will be 1. Because of course, for any value of x, the amplitude appears as the angle in both these functions. Okay. And let me mention the double periodicity. But because I told you before, I can just give you the values. So let me write k as k of m, and let me write k prime to mean k evaluated at 1 minus m. Okay, and if this is true, then all the functions have both real period and imaginary period that are either a multiple of, the real periods are multiples of k, but it could be 2k or 4k. And the imaginary periods are also multiples of these other k that I'm going to call k prime. K evaluated at 1 minus n. Again, it could be 2k or 4k in the imaginary direction. Let me give you the expression and we go to lunch. The sign of x plus an even multiple of the value of k and another even multiple times I, the value k prime, this number k prime, is always equal to plus or minus, depending on n, the sign of x. So that means Sn repeats both if you move in the real axis and in the imaginary axis. And if you move half the period also, it just changes sign as some kind of odd function. And for the k9, if I write the same, 2nk plus 2n prime I k prime here, n and prime can be any integers unrelated. So again, if I move to a point like this, it will give me the same function with the same period in both directions. The k9 of x. So well, this minus is important because it tells me that this 9 has an imaginary period of only 2i k prime, but a real period of 4k, and the k9 has 4k and 4k prime in both directions, and the d9 we have the opposite. We got 2k and 4k prime, so we can represent it like this. Evaluated at x plus 2n k plus 2n prime I k prime, I get minus to the power of n prime times the function at x. And well, here, of course, all of these functions should have a slash n, but it's I'm just do it for simplicity. Okay, let me give you these equations. I don't need to prove them because if I give you this assignment, well, actually, I didn't give you assignment about the last gamma and beta topic, right? So, but anyway, just to finish this topic, let me give you the equation for the derivative of the S9. Just I don't write the x and the n because you understand that this is just a function of x and n. The derivative of the S9 is the k9 multiplied by the 9. The derivative of the k9 is minus the S9 multiplied by the 9. And the derivative of the 9 is just minus n multiplied by the S9 multiplied by the 10. When I say that all of them sound the same, hopefully you can see it on the whiteboard and you can look through it. Okay. So, well, the same as with the hyperbolic and trigonometric functions, the derivatives of the elliptic functions also are elliptic functions or combinations of elliptic functions. Okay, which again, let's stop here. Again, as I said, I'm not completely sure of where a physicist would use this, but I think it's an interesting generalization that may arise in problems that involve some integrals. Like when the symmetry is broken, like what happens with the ellipse when a circle becomes an ellipse. But it can happen in other cases where something is distorted. Anyway, let's stop here. Thank you. Oh, maybe I will record this also. So people who watch the recording also know. Next week, we will start the class at 9:30. Okay. I hope everyone is okay with that. Does anyone have class in the afternoon? You don't have class in the afternoon, right? Yes. Okay. So yeah, if you don't mind, then we will start at 9:30 and end at 12:30. That's okay. For next week and the following weeks, okay? So that people can have take the shuttle bus. Thank you.